Okay, this will be your last lesson before assignment 5. And in this lesson, we are going to have a look at how you know which model to use if you're trying to find a curve of best fit for a set of data. So our choices so far are linear, quadratic, or exponential. And as we've seen, when you're just looking at the graph, it can be difficult to know which model will suit the data best. So one way certainly is by looking at the table of values. Okay, so let's do a quick review of what we know about the tables for these three types. We know that in the table of a linear function, the that doesn't look very good. Let's try that again. We know that in the table of a linear function, the first differences are constant. So first differences constant. Okay, so for example, if I had a table such as this one, where my y values are, say, 7, 4, 1, -2, -5, I can see that as I go through my y column, I'm going down by 3 every time, or I'm subtracting 3 each time. Okay, so that one would definitely have, the closest would be a linear model. And so sometimes your first differences won't be exactly the same, but if they're very, very close, then it's quite possible that a line of best fit would be the best fit for your data. With quadratics, it's the second differences that would be the same or very, very close. Okay, so if I had a table such as this one, where my y values are 6, 3, 2, 3, and 6. Okay, then my first differences, so from 6 to 3, we go down 3. From 3 to 2, we go down 1. From 2 to 3 is up 1, and from 3 to 6 is up 3. So it's not linear. Okay, then if I find my second differences, from -3 to -1 is an increase of 2. From -1 to 1 is as well, and from 1 to 3, also an increase of 2. So I know that that one is quadratic. And for exponential curves, what I'm looking at in the table is that there is a common ratio. And that basically means that I'm multiplying or dividing by the same number in each case. So an example of that would be this table here, where my y values would be 4, 8, 16, 32, 64. So I can clearly see that in the y column, we are multiplying by 2. That is, the numbers are doubling each time. Okay, so one way is by looking at the table to determine which one seems to be the closest. But a better way is to use the correlation coefficient, which we've talked about before. So the correlation coefficient tells you how well your model suits your data. So the closer that value is to 1 or -1, the better the fit. So in this next example, we are given a table that tells us the mass of debris in orbit around the Earth for the years between 1990 and 1995. And what we want to do is find a model to represent this data so we could make predictions about what the mass of debris would be years later, assuming that the trend in the table held constant, which it may or may not, of course. So what you're going to do is get a graphing calculator, so you'll need to do this one at school. And one thing I've made note of here for you is that when you are entering your data, consider entering the years since 1990 as your first variable. So what I mean by that is when you go to enter your data into your lists, okay, consider your x variable to represent the number of years since 1990 instead of the actual year itself. So for 1990, we'll enter a 0, 1991, we'll enter a 1, and so on. okay, just to make the numbers in your equation a little bit easier to work with. So your y, or your list 2, will be your y values, and they'll be as written in the table, but you're just going to make some adjustments to your year column and make that years since 1990. So we're going to adjust those values there. Okay, and what you're going to do next then is you're going to determine a linear, a quadratic, and an exponential model for the data. So you're going to find your instructions for regression, and you're going to go through that process 3 times. You only have to enter the data once. Okay, and then you're going to go through and do a linear regression, followed by a quadratic, followed by an exponential. And notice I've said here, record the correlation coefficient beside each equation, because that's how you're going to determine which one is the best fit. Okay, once you have the equations, you are asked to answer 3 questions that follow, okay, using the model. So using each model means use the equation. Okay, so once you have your equation, it says use each model to predict the mass of space debris in 2005. Now remember that 2005 is 15 years after 1990. So when you use your equation, you're going to let x equal 15, as in 15 years after 1990. Okay, then it asks you which model is the most optimistic, as in which one would predict we would have the least amount of space debris, and which one is the most pessimistic, so which one predicts we will have the most space debris, and then which one fits the data best. For that, you're going to look at your correlation coefficient. Okay, but other than that, you're going to go through this example independently. But when you are finished, you may ask me to see the solutions to make sure that you got the right equations there, okay? And I can help you if you have difficulty. All right, and that concludes this lesson.